Hello students. Today we will discuss about overcurrent relay. In the last lecture we discussed about the relays basics, and I have mentioned over there that we will discuss different type of relays in our upcoming lectures. So for this time we are discussing overcurrent relay. This is part 2 from the relay section, and overall from the section of power system protection it is lecture number 4. Before studying any type of relay, the protection scheme must need to be studied. Protection scheme can be divided into two major groupings. One is unit scheme and the other is non-unit scheme. Well, in unit type protection, we can say unit type schemes protect a specific area of the system. You can say transformer, transmission line, generator, or bus bar. So any deviation from this must indicate an abnormal current path. In these schemes, the effects of any disturbance or operating condition outside the area of interest are totally ignored, and the protection must be designed to be stable above the maximum possible fault current that could be flow through the protected area. I must mention that the unit protection scheme is based on KCL, that is Kirchhoff's current law, uh, that you have studied earlier, uh, who says the sum of the currents entering any node or leaving any node must be 0. So this is unit scheme. And about the non-unit type protection, uh, the non-unit schemes, while also intended to protect the specific areas, have no fixed boundaries, uh, as well as protecting their own designated areas. The protective zones can overlap in other areas, while this can be beneficial for backup purposes. There can be a tendency for too great an area to be isolated if a fault is detected by different non-unit schemes. Uh, the most simple of these schemes measure currents and incorporates an inverse time characteristics into protection operation to allow protection nearer to the fault to operate first. We can also say that the non-unit type protection isolate uh, a single area from a big chunk. If we divide the non-unit type protection system, we can say it is divided into three major schemes. Number one is the time graded over current protection. Number two is current graded over current protection. And number three is distance or impedance based protection. Um, we can also say that if we discriminate our systems, for example, by time, by current, or by distance, these three are different dimensions in which we can use the protection system according to our need. So we are studying overcurrent relay. If we define simply what is overcurrent relay, so it is basically defined as the relay which operates only when the value of the current is greater than relay setting time. It protects the equipment of power system from the fault currents. Remember students, the overcurrent relay is the most widely used relay in industries. Well, as we mentioned the overcurrent relay basic definition in the last slide, so we must say that overcurrent protection protects electrical power system against excessive current. which are caused by short circuits, ground faults. Overcurrent relays can be used to protect practically any power system elements that can be transmission lines, transformers, generators, or motors. For feeder protection, there would be more than one overcurrent relay to protect different sections of the feeder. These overcurrent relays need to coordinate with each other such that relay nearest fault operate first. Use time, current, and a combination of both time and current are three ways to discriminate adjacent overcurrent relay, as we mentioned earlier. The overcurrent relays give protection against phase fault, earth faults, and winding faults. Well, short circuit currents are generally, uh, as you can say, several times 5 to 20 time of full load current. Hence, fault fast clearance is always desirable on short circuits to avoid the maximum damage. If we talk about the major purpose of the overcurrent protections, so we can say that it detect abnormal conditions like faults, and it basically isolate faulty part of the system, like we mentioned in the non-unit protection scheme. Along with that, speed fast operation to minimize damage and danger. Discrimination, isolate only the faulty section. Dependability and reliability. Security, stability, and cost of protection. Well, these all are the purposes of the overcurrent protection. Uh, you can say, uh, if the fault is not diagnosed properly, so it will damage the whole system, and in the consequences, the cost uh, the cost and the other damages the industry have to bear. So as per the speed of operation is concerned, um, as we study in the last lecture, that if the speed of operation is not quick, so the damage will increase drastically. Overcurrent relay ratings. In order for an overcurrent protection device to operate properly, overcurrent protective device rating must be properly selected. These ratings include voltage, ampere, and interrupting ratings. Well, voltage and ampere are the two main factors. If we can say that current limiting can be considered as another overcurrent protective device rating, although not all overcurrent protective devices are required to have this characteristic. So, if we divide into two sections, for that we can say, if we talk about voltage rating, the voltage rating of the overcurrent protective device must be at least equal to or greater than the circuit voltage. The overcurrent protective device rating can be higher than the system voltage but never low. Same as the ampere rating, the ampere rating of overcurrent protecting device normally should not exceed the current carrying capacity of the conductor. As a general rule, the ampere rating of the overcurrent protecting device is selected at 125% of the continuous load currents. Well, these all ratings you can get from the data sheet of the relays, and now almost when you design the system, you define all these parameters according to your needs, and on the basis of that needs, you select your overcurrent relay. Difference between overcurrent and overload protection. Well, these are the two terms in which students get confused sometimes, so we can differentiate what is overcurrent and what is overload protection. So we can say that overcurrent protection protects against excessive current or currents beyond the acceptable current ratings, which are resulting from short circuits, ground faults, and other conditions. While the overload protection protects against the situation where overload current causes overheating of the protected equipment. The overcurrent protection is a bigger concept, so that overload protection can be considered as a subset of um, overcurrent protection. The overcurrent relay can be used as overload protection when protect the resistive loads. Uh, for example, if I will give you like the motors we have, if the winding of the motor it get heat, so we can say it will lie in the overload protection. So when the winding get heats, so there is a clear chance that it may be burns out. So in that category we can say that is overload protection. And as you mentioned earlier, that uh, the overload protection is the subset of overcurrent protection, because as a basic concept we knows that if the current flows from any wire, it produce heat. There are some type of setting that we have to do while operating any relay. So if we talk about the overcurrent relay, there are some settings in an electromechanical relays. We have the TMS, and that is time multiplier setting. You can say the time multiplier setting decides the operating time of the relay, while it adjusts the travel of aluminum disc. The working of that electromagnetic uh, overcurrent relay we will see in next slides. So in other words, we can say that the user will decide, and on the basis of calculation, that on which operating time he want to operate. Second, there is a term called plug setting. Well, the plug setting decides the current required for relay to pick up. As the name suggests, the plug setting comes from the fact that in these relays we have insert a shortening plug in the plug setting bridge so as to change the number of turns of the operating coil to get a particular pickup value. Uh, for phase fault relay, a typical value is 0.5 to 2, or for earth fault relays, its typical value is zero point 0.2 to zero point 0.8. Well, there are two more terminologies like relay pickup current. You can say the minimum current required for the relay to activate. So it can say that I pickup is equal to IS into PS, where PS is the plug setting and IS is the CT rated secondary current. Um as we studied in reliability and sensitivity sections, you can say that relay is a device that needs to be activate on time. If it activates before time or after a certain time, so it will get damage the unit or plant that in which it is installed in both section. The second one is the plug setting multiplier, that is PSM. So basically it is the ratio between the relay current and the pickup current, where The relay current is the current through relay operating coil. So, as per standard, the PSM, that is plug setting multiplier, less than 1 means that the normal current load is flowing at PSM greater than 1, the relay is supposed to pick up. Higher values of PSM indicates the how the serious fault is, because if we can say on the formula we can see that PSM is equal to um, relay current over the pickup current. Well, as I mentioned that we are discussing the electromechanical relay, overcurrent relay. So if we talk about the principle, the relay monitoring is based on the current, and it has inverse characteristic with respect to the currents being monitored. This electromechanical relay is without doubt one of the most popular relay used on medium and low voltage systems for many years. If we talk about the principle on which this electromechanical relay based, as you can see on the figure, uh, the torque is produced by two alternating flux acting on a common metallic but non-magnetic rotor. Well, this plate is the aluminum disc that we also mentioned in our TMS setting, the time multiplier setting. So we can say the two fluxes which are represented by eta 1 and 2 having a phase difference of theta between them. So each flux induce a voltage in the disk and hence gives rise to induce eddy currents. That currents can be known as I eta 1 and I eta 2. Lenz's law, uh, which says if an induced current flows, its direction is always such that it will oppose the change of flux that produce it. Since the eddy current path has negligible inductance, so they are in phase with the induced voltages. Uh, well, the complete derivation for the torque and force are mentioned in handouts. You can refer from there. Well, if we talk about the construction of this electromechanical relay, so there are some basics. On the top, you can see the TMS adjustment dial, that is time multiplier setting, uh, which we have studied in the last slides. One more is shading coil, aluminum disc that we have studied in the last slide. Along with that, it has the control spring, permanent magnet, movable contact, and iron core. From its structure, one thing is very evident that its construction is just like the energy meter. So, if we can see in the figure, uh, there are two fluxes shifted in time phases are obtained from the input current by using a shading coil. The flux in the shaded coils lag the main flux. Uh, the torque thus produced by the interaction of the two fluxes, neglecting saturation, that is proportional to the I square, that is the current. Well, this is the deflecting torque that you can denote with T deflecting. The spiral spring provides the control torque that you can depict it from T controlling. Well, the control torque can be considered to be directly proportional to the angle through which backstop has been retarded from the trip position. Well, the role of the permanent magnet is that it provides the damping torque, which is active only when the disk is in motion and is thus proportional to the rate of change of angle. Students, the complete description and construction details are mentioned in handouts also. You can refer from there. The overcurrent relay has different types that is specified on the basis of its operation. So if we can say the number one is instantaneous overcurrent relay, and number two is defined time overcurrent relay, number three is inverse time overcurrent relay that we have discussed, IDMT relay. It has three subtypes, that is moderately inverse, very inverse, and extremely inverse. And number four is directional overcurrent relay. In next slides, we will discuss each of this type in detail. First type is instantaneous overcurrent relay. An instantaneous overcurrent relay is one in which no intentional time delay is provided for operation. In such a relay, uh, the relay contacts close immediately after the current in the relay coil exceeds that for which it is set. Uh, well, as the name suggests, that is instantaneous. So, in which we cannot count that time, which is the operating time. Well, if we talk about some major features of instantaneous overcurrent relay, number one, I can say that operates in a definite time when the current exceeds its pickup value. Its operation criterion is the only current magnitude without time delay. There is no intentional time delay. Along with that, the coordination of definite current relay is based on the fact that the fault current varies with the position of the fault because of the difference in the impedance between the fault and the source. Uh, the relay located furthest from the source operate for a low current value. Uh, well, the operating time is zero point 0.1 second or less. Well, this type of relay, that is instantaneous overcurrent relay, is applied on the basically the outgoing feeders. The next one is defined time overcurrent relay. In this type, two conditions must be satisfied for the operation. That is, of course, the tripping operation. Number one is current must exceed the setting values and the fault must be continuous at least a time equal to the time setting of the relay. As you can see in the graph is between the time and the current. The major feature of this relay its adjustability that you cannot see in the instantaneous relay. Well, you can adjust it according to the its as per need. Well, if we talk about some major features of the definite time overcurrent relay, you can say for operation of definite time overcurrent relay, operating time is constant. Secondly, its operation is independent of the magnitude of the current above the pickup value, that is I pickup. Uh, Next, it has pickup and time dial setting. Desired time delay can be set with the help of an intentional time delay mechanism. This is the feature that I am discussing in the last slide. Uh, you can also say the constant tripping time is independent of in feed variation and fault location. There are some drawbacks also. A few of them are I'm mentioning. The continuity in the supply cannot be maintained at the load end in the event of fault. Uh, Time lag is provided, which is not desirable in on short circuits. Along with that, It is difficult to coordinate and requires changes with the addition of load. Uh, and the last relay have difficulties in distinguishing between fault currents at one point or another when faults impedances between these points are small. So we can say it has the poor discrimination quality. Mention some applications of the definite time overcurrent relay. Uh, it is used in backup protection of distance relay of transmission lines with time delay, backup protection of the differential relay of the power transformer with time delay, and the main protection to outgoing feeders and bus couplers with uh, adjustable time delay settings. Well, some of the features and relay you are not familiar with it now, but in the upcoming lectures we are discussing these distance relay and differential relay also. The third one is inverse definite time minimum time overcurrent relay. Well, this is possibly the most widely used characteristic in this overcurrent relay. The characteristic is the inverse in the initial part, which tend to definite minimum operating time as the current becomes very high. Well, the reason for the operating time becoming definite minimum at high values of the current is that in the electromechanical relays, the flux saturates at high value of the current, and the relay operating torque, which is proportional to the square of the flux, does not increase substantially after the saturation sets in. Well, the mathematical relation between the current and the operating time of the IDMT characteristics can be written as uh, for example, this T operating is depicting the operation time of the relay. Zero point 0.4 is the factor, and TMS is that factor that is time multiplier setting that you have studied in the previous slides, and PSM is a plug setting multiplier. So, uh, by inserting uh, the data of TMS and PSM, you can find out the operating time of this IDMT relay. Well, if we talk about some major features of this IDMT relay, like other that it operates when current exceeds its backup value, or operating time depends on the magnitude of the current. Most importantly, it gives inverse time characteristic at lower values of the fault current and definite time characteristic at higher value. This is the most important feature of this IDMT relay. Well, an inverse characteristics is obtained if the value of the plug setting, that is PSM, is below 10. For the values of 10 and 20, characteristic tends towards the definite time characteristic. Well, this relay is widely used for the protection of the distribution lines. Well, based on the inverseness, it has three different types. Number one is normal inverse time over current relay. Uh, well, it's used when the fault current is dependent on generation of fault, not fault location. So we can say that if you want to trace the fault location, so this relay will not help. The accuracy of the operating time may range from 5 to 7.5 of the nominal operating time as specified in the uh, relevant norms. Uh, as applications are concerned, most frequently used in utility and industrial circuits, especially applicable where the fault magnitude is mainly dependent on the system generating capacity at the time of fault. Next one is very inverse time over current relay. It gives more inverse characteristic than that of IDMT. It also used where there is a reduction in fault current as the distance from the source increases. Along with that, very inverse overcurrent relays are particularly suitable if the short circuit current drops rapidly with the distance from the substation. Well, the grading margin may be reduced to a value in the range between zero point 0.3 to zero point 0.4 seconds. It is used when the fault current is depending on fault location. Along with that, it is also used when the fault current is independent of the normal changes in generating capacity. One more type is extremely inverse time overcurrent relay. The difference is it has more inverse characteristic than that of IDMT and very inverse overcurrent relay. It is suitable for the protection of machines against overheating. You can also say the overloading. The use of the extremely inverse overcurrent relay makes it possible to use a short time delay in spite of high switching in currents. Uh, as per its operating time formula is concerned, you can say if you enter the TMS and PSM setting numbers, you will achieve this operating time. More type is directional overcurrent relay. Uh, when the power system is not radial, as you read in power distribution system, you have three systems: the interconnected system, radial system. So when your system is not radial, you can see the source on one side of the line. An overcurrent relay may not be able to provide adequate protection. This type of relay operates in on direction of the current flow and blocks in the opposite direction. Three conditions must be satisfied for its operation: current magnitude, time delay, and directionality. Uh, the directionality of the current flow can be identified using voltage as a reference of direction. Uh, the graph basically shows the characteristic of IDMT relay. As we mentioned, the extremely inverse, very inverse, and simple IDMT. The graph is basically between the operating time and plug setting multiplier. So the formulas we have discussed in our last slides for extremely inverse and very inverse and IDMT relay case. Uh, if you can put the TMS 1, so you can vary the PSM value and you can achieve different operating times. So in this graph you can see the extremely inverse operating time, uh, very inverse relay operating time, and IDMT relay time are both different from each other. So you can verify yourself by putting different values in this formula that is given in the last slides. Well, if we talk about specifically some of the applications of overcurrent relay that I think is very necessary to understand the complete operation of this overcurrent relay in our daily life or in industrial use. So, if we talk about motor protection, so we can say that it is basically used against the overloads and short circuits in the stator windings of the motor. Inverse time and instantaneous overcurrent phase and ground. Overcurrent relay that is used for motor protection is above 1000 kilowatt. So if we talk about transformer protection, so it is used only when the cost of overcurrent relays are not justified extensively, also at power transformer location for external fault and backup protection. If we talk about line protection, on some transmission line where the cost of distance relaying cannot be justified, we can use along with that primary ground fault protection on most of the transmission lines where distance relay are used for phase fault. Uh, you can also say for ground backup protection on the most lines having pilot relaying for the primary protection. In distribution protection, the overcurrent relaying is very well suited to the distribution system protection for the following reason. Well, it is basically simple and inexpensive, and along with that, the operation is very simple. Very often, the relays do not need to be directional, hence, no PT or power transformer supply is required. It is possible to use a set of two overcurrent relays for the protection against interface faults and a separate overcurrent relay for ground faults. That's all from the overcurrent relay section. In next lecture, we will discuss some other type of relay. Thank you very much.